Okay, so the final part of our chapter on probability involves looking at probability and what we call the normal distribution. Okay, now normal distribution of what? The normal distribution of data. And if you're wondering about what is the normal distribution of data, the answer is anything that's controlled by humans or anything that's controlled by nature. So the normal distribution could also be called a natural distribution, which I'll show you in a moment. But just in case you're wondering why I'm showing you this, what we call a Galton board here. This Galton board involves nothing more than successive rows of pegs, 1, 2, 3, 4, and so on, down through which you simply drop spheres. Okay, and these spheres, when they hit a peg, have an equal probability of bouncing left and right. So therefore, the probability of left or right is equal. All right, so there's a normal distribution of probability, 50-50 every time you hit a peg. But the interesting thing is that as we allow these little spheres to drop, a very unusual picture builds up at the bottom. And here's what I want to show you. Here's the picture. You get something like that, which is nothing more than a lovely symmetrical curve. Okay, now just to prove that this actually works, let me take you to this site. You can go here yourselves and you can try this out. Two things I want to show you. So let's take a look at it here. It'll work for us now. There it is. And I'm going to put on, let me just pause that now. Let me just put up, we put 9 lines. So restart this and let me speed this up a little bit. Okay, now watch the bottom. There's a tendency for these spheres to gather around the center. Now that's extremely important, okay? And the more of these I allow in, the greater the collection around the center. Where do I see the least amount of collection? The least amount of collection of these spheres is the extreme left and the extreme right, which are both, if you look at them at the moment, they're both at 0, okay? So just let it build up a little bit, and you'll notice that there's a tendency for these spheres to fall down the middle. Now the longer I leave this thing, the more into a perfect symmetrical curve it builds. Let me just speed it up. We're going to start it again, and I'm just going to cut back on the number of lines here. So restart. Let's see if we can get a better curve this time. Okay, so again you see the same thing. There's a symmetry around the center. Now when I get the symmetry hit, I'm going to pause it. Just keep watching the middle. There's a tendency of the data to accumulate symmetrically around the center. Okay, so again you'll notice you've got that curve. You've got that symmetrical curve. Okay, just like that. And again, I stop there now. There you notice the curve has built itself. Okay, so it doesn't matter how many of these spheres we drop, how many layers of pegs they have to go through. There seems to be a pattern emerging here that normal or naturally distributed data seems to congregate around the center. Now at the center of every set of numbers or every set of data is the mean, it's the calculated center. So data has a tendency to cling or to gather around the mean, and it has less of a tendency to deviate from the mean. So that's the reason why we get a very high success rate of collecting these spheres at the center and very little success rate at the extreme left and the extreme right. Okay, we'll come back to that again later. So this Galton board, we said already, nothing more than layers of pegs down through which you drop spheres. When you drop these little spheres, they're collected. And as they are collected, they seem to gather around the center. Now that's the key thing. So they seem to gather around the center, where they form a symmetrical gathering around the center. That symmetrical gathering is important. Each time the ball hits one of the pegs, it bounces either left or right with the same probability. Okay, that's the key thing. So when there's an equal chance of bouncing left or right, the balls collected in the bins form the classic bell-shaped curve of the normal distribution. Now, there's the sign again, or there's the term again, the normal distribution, the natural distribution, meaning no interference. It's just the way these things fall. But can I interfere in statistics? Of course I can. Let's do this again. Let's go back to this site. And this time, let me skew the data. But in order to skew the data, I have to do something, okay? So watch this carefully. Now, do you see up here? There's a 50-50 chance of these little spheres, every time they hit in the peg, going left or right. I'm now going to deviate that in favor of the right-hand side. So I'm now going to have it a 75-35. Oh, sorry, 75-25. Now watch what happens. Let's speed it up. Now there's a greater tendency for these things to gather on the right hand side because I skewed the data. I interfered. Okay, if things are left alone, if nature's allowed to take her course, then there will always be a distribution of statistics or data which are symmetrical around a central value, and that central value is what we call the mean. Okay, oops, daisy. So when the probabilities are not even, as I showed you a moment ago, we get a nice skewed version of the normal distribution. Now here's three examples of skewed data. The first two, even though they're skewed away from the center, they still have a name. This one here is what we call negatively skewed data, and this one here is positively skewed data. If you're wondering why they're called negatively skewed and positively skewed, it's the tail. That tail goes off into the negative region, that tail goes off into the positive region. Okay, so that's positively skewed, and this one here is negatively skewed. And this one here, the third one, doesn't tell us any picture at all. It just looks like there's a random collection of data that doesn't seem to have any pattern, doesn't seem to have any type of story behind it, so it's certainly not normally or naturally distributed data. Okay, there are many cases where the data, instead of being skewed, just falls, as we showed you a moment ago at the Galton board, symmetrically around a central value. And when the data gathers around a central value, it is a normal distribution which looks like this. Okay, so again you'll notice that we have central value, there it is, around which the data seems to be gathered symmetrical. Now why is it called a bell-shaped curve? Well, the only reason why I can think it's called a bell-shaped curve is because if you do this and this and this and this, you get a bell, like Christmas. Okay, so that's why it's called a bell-shaped curve. You might hear it sometimes called a bell-shaped curve or a normal distribution curve. They're both the same thing. Many things closely follow a normal distribution. Now, for what? For example, anything that is genetic. So blood pressure, height, weight, IQ, all of these things are controlled by nature. Nature distributes her data in a very normal manner. And that means then that as we take any statistic in the human population, we're going to get that same shape. We're going to get a central value, which is the average or the mean, around which all the other values tend to congregate. Okay, and as they move away, less and less values will go further away from that central value. So the heights of people, for example, like that. So there you have a range of people and a range of different heights. And again, if you were to take the heights of 150 to 300 people and put them all into some type of statistical arrangement, you'd get the normal curve because height is controlled by genetics. Nature has a hand. The size of things that are produced by machines. Now you might say, hold on a sec, there's no machine, there's no humans, no genetics here. But think about it, who programs the machine? To program the machine, there has to be human input. Where there's human input, there's going to be tiny errors always, okay? But the errors themselves are distributed normally by the machine. So therefore, you will still get a situation where if you wanted a machine to make rods of iron that were 40 millimeters in length, there'll be tiny variations. Most of them will be in and around the 40, but very few then will be less than the 40 by a big amount or greater than 40 by a big amount. So you're still going to get exactly the same type of curve. Errors in measurement. To err is human. We make mistakes every time we measure anything, particularly if we're measuring with our eyes. Blood pressure, again, we would say it's normally distributed. And finally, the marks on a test, which are linked to IQ. Now, just a word about IQ. Let's just take a look and see, how is IQ distributed in the human population? Well, there's an idea of how it's distributed. From this graph, there are two things we can tell. The first thing I can tell is that this particular population of people has a mean IQ of 100. See that? So that's the mean, the middle, and it's the calculated middle. And then everybody else who doesn't have an IQ of 100 is deviated from that mean. Now, some people might be very slightly deviated. So people with an IQ of 101 or 102, 105, for example, be there and there. Okay, 105. So they're not too far away from the mean. But what this also tells me is that the further away from the mean IQ we go, the less people we find. So there are very, very few, if any, people that have an IQ of 150 or greater. And there are very, very few, if any, people who have an IQ of 50 or less. The majority of the population will be somewhere in the region of 60 to 140. And that will cover up to 99.7% of the population. So 99.7% of every human being, all the population in this area, roughly between 60 and 140. Okay, so what two things does this tell me again? It tells me that there is a mean IQ, and the mean IQ, you can see from here, is 100. Okay, what it also tells me is that the further away from 100 we go on either side, the less people we will find, to the point where we can physically say there's practically very little, if any, people with greater than 150 IQ, and very few people, if any, with an IQ of less than 50. The normal distribution has certain characteristics. Number one, the mean, the mode, and the median are the same. Now, you might remember these from your junior cert. The mean, the median, and the mode are measures of centre. Okay? That's why we don't talk about the average. The average is a group name. The mean is the calculated middle. You calculate it mathematically. The median is the physical middle, where you put your finger slap bang on the middle value. And the mode is the object or the objects that appear most frequently in a given set of numbers or objects. Okay, so this one here is calculated, this one here is physical, and this one here is the one that's on popularity, the one that occurs most frequently. Okay, and they're all measures of centre, but the one that we're going to be interested in as far as the normal curve is concerned is the mean. However, because it's symmetrical, the mean, the mode, and the median are in the same place. They're all in the centre. Secondly, the normal distribution has wonderful symmetry, and this is extremely important, and it's going to come back and help us mathematically later on. But there's a symmetry around the mean. So therefore, we can take the mean down the middle. Symmetry means 50% of the population will be on the left-hand side of the mean, and 50% of the population will be on the right-hand side of the mean. There you go, like that. So you have your mean, mode, and median slapped down the middle. Then you've got 50% deviated to the left, 50% deviated to the right. The more to the right-hand side we go, the greater than the average value we are, the mean value. The further to the left-hand side we go, the less than the mean value we are. So that's just the curve as we're going to be using later on. Now, when we roll a pair of die, and think about it, a pair of dice, take two dice, okay? There's 1 to 6 on both of them. If you take a pair of die and you throw them and you look at the numbers that they produce, how many possible outcomes are there? Well, to speed things up, there are 36. The first die is green, the second die is red, okay? Here's all the possible combinations of what can turn up when I throw these die. You can get a double 1, a double 2, a double 3, and so on. You can get a 1 and a 2, or a 2 and a 1. But here's the lovely thing even about this. The normal curve is present. Now, I don't know whether you can see it or not, but the normal curve is in there. And here's what I'm going to ask you. What's the probability of throwing two die and getting a sum of 2? Now, take a look at the table. Where do the two die give me a sum of 2? The answer is here. There's only one square out of all these 36 squares that add up to 2. So therefore, the probability of getting a sum of 2 is 1 out of the 36. What about the probability of getting a 3? Well, you could get a 2 and a 1, or a 1 and a 2. So there they are. That's a 2 out of 36. Getting a 3 and getting a 4 is this one here. So they are 3 out of 36. Getting a 5 is there. They're all on the diagonals, you see, which is 4 over 36. Getting a 6 is 5 over 36. Getting a 7 is 6 over 36. And I'm going to stop. Because if I was to ask you, what's the probability of the two dice adding to 8? You'd say to me, oh, look, there it is there. It's 5 over 36. What about getting a 9? 4 out of 36. Getting a 10? 3 out of 36. Getting an 11? 2 out of 36. Getting a 12? 1 out of 36. So in other words, it goes 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. You get a beautiful symmetrical curve again. So even in a pair of die, it is possible for me to build a normal curve if I take a look and see what are the probabilities of getting a 2 or a 3 or a 4 as a sum of the numbers that appear on the two dice. So if I take all those outputs, yeah, there's one way to get 2, there are 2 ways to get 3, there are 3 ways to get 4. What does it look like if I graph them? Well, it looks something like this. So there's your probability of throwing a sum of 2, which we said already is 1 out of 36, yeah? Then you have 2 out of 36. then 3 out of 36. Now these decimals over here, they just represent the same probability in decimal form. Then 4 over 36, 5 over 36, and how are we getting a 7? 6 out of 36. Getting an 8, 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36. So I've plotted the probabilities of a particular outcome. What do I get? I get that lovely symmetrical normal curve. Where's the mean? There's the mean. Okay. Now, how many outcomes are to the left? 50% of them. How many outcomes are to the right? 50% of them. So even in a pair of dice, when you take all the possible sums of all the outcomes, you end up getting a normally distributed set of data, providing that both die are fair. Okay, there's no little weights hidden them or anything like that, that they're free to give any number they want. They will always give you the normal curve. The previous example with dice produced what we call discrete data. Now, I hope you can remember the difference between discrete and continuous data. Discrete data is data that only has certain values. So, for example, if you go in to buy a pair of shoes, you can only buy a pair of shoes at certain numbers. You can't go in and ask for a size 6.2897 because they wouldn't have them. Okay, they've got a 4, 4.5, 5, 5.5, 6, 6.5, 7, 7.5, and so on. But you don't have anything in between those. So you can't get a 7 3/4 or 7 7/8. They don't exist. So discrete data simply means definite values. Okay, there will be values that you cannot get. Dress sizes, shoe sizes, and so on. However, when we use discrete data, we get the rugged type of normal curve. But when we use continuous data, say for example you take somebody's height, from the moment that they start walking to the time that they reach their 21st or 22nd birthday, okay? So you measure them almost every week over those number of years. Is there any height between the lowest and the highest that they won't be? Don't they cover every single height from the moment they're 2 to the time they're 21? They don't skip a height. You don't go to bed at 4'2" and wake up with 4'6" overnight. That doesn't happen. You go through every single one of those values from the smallest height to the biggest height that you achieve in adulthood. So that's continuous. Continuous means that every possible value is available. Okay, so any value in a given range. Now, here's the interesting thing. Body mass, body height, IQ, all these things, they're all continuous data. They can be any value between the two bookends of whatever, 1 in 100 or 1 in 20, whatever it's going to be. And if we plot continuous data, we still get the same normal curve, but it smooths out into something like this. All right. Now, again, what do you notice here? You notice here that there's a mean. And the mean, as we can see here, is £200. So in this particular group of people, you have 50% of them that have a mean of £200. And then you'll notice that 50% of the population go this way, up to a body weight of £300. 50% go down this way to a body weight of £100. And we also notice that there are very, very few people with a body weight of £100 and very, very few people in this particular sample with a body weight of £300. It is symmetrically gathered around the central mean, the data that's here. Okay. In any body of natural occurring or normally distributed data, there is a mean, which is one measure of the center of the data. We've spoken about that already. If you do not have the mean value, then you're deviated from the mean. And the further away from the mean value are, the more deviated you will become. The standard deviation is a measure of how the data is spread around the mean and is represented by the symbol sigma. Okay. Now, sigma is a value that is taken as being a chunk of data either side of the mean. Okay. And it is a chunk of data that is repeated. And the one thing that we notice is this, that we normally take 3 deviations either side of the mean, left and right, okay, to divide up our table. I'll explain what that means now. For example, take this chart here. First of all, are pizza delivery times normally distributed? The answer is yes. Okay. Question 1, what's the mean delivery time? Well, the mean delivery time here seems to be 30 minutes. So the mean delivery time is 30 minutes. Now notice that there's only certain values we're looking at. So we're looking at 35, 40, 45, 25, 20, and 15. Okay. So we're looking at 3 deviations above the mean, 3 deviations below the mean. The standard deviation is 5 minutes. So in other words, 30 to 35 is 1 deviation. 30 to 40 is 2 deviations. 30 to 45 is 3 deviations. And likewise, that's 1 deviation this way, backwards, 5 minutes. Then we've got another deviation 10 minutes this way. Then 15 minutes is another deviation there. Okay, so if we take the mean as being 30, what I can say here is that I have standardized the deviation. I've spread it equally around either side of the mean. Normally, we take 3 standard deviations, okay? And the standard deviation has a value, and it's the number of units that the first deviation is away from the mean. It's the number of units that the second deviation is away from the first one, and so on. So that's what these graphs tell us. So for example, normal distribution intelligent quotient. Now, what does that mean? That's IQ, okay? How do I read this table? Well, first of all, here is the mean. So there's a mean of 100, okay? So there's an IQ mean of 100. Now, what's the standard deviation? Sigma. The standard deviation is the number of units between the mean and the first bar either side of the mean. So if I go from there to there, or there to there, what do I notice? There are 15 units either side. And if I go from there to there, that's another 15. And even from there to there, that's another 15. So I have standardized the deviation into 3 bundles either side of the mean of 15 units each. Okay, so if I take the mean plus or minus 1 standard deviation, what does that do? That gives me a range. The mean is 100, plus or minus 1 standard deviation, that goes between 85 and 115. What about the mean plus or minus 2 standard deviations? What does that give me? Well, that's going to give me 70 up to 130. And finally, what's the mean plus or minus 3 standard deviations? And the answer is between 55 and 145. So there are 3 areas that we are going to have to focus on. First of all, the mean. Okay, that's the most important one. Then 1 standard deviation either side of the mean. Then 2 standard deviations either side of the mean. Then 3 standard deviations either side of the mean. And you might say to yourself, why do we look at that? And the answer is because of the number of people it catches. Okay, for example, if you start at the mean and you go 1 standard deviation either side, you end up catching 66% of the population. If you go 2 standard deviations either side of the mean, you get 97% of the population. And if you go 3 standard deviations either side of the mean, you get 99.8% of the population. Okay, so the reason why they use 3 standard deviations either side of the mean is in order to chop this symmetrical normal curve into regions of population: 66%, 97% and 99.8%. Okay, so let's take a look at this. We said already what's the mean IQ. In this case, the mean IQ is the one down the middle, it's 100. And what's the standard deviation? In other words, in the 3 regions left and right, how many units are between the regions left and right? And the answer here is 15. So here's the empirical rule, as we said already. It is found that 68% of all data lies within plus or minus 1 standard deviation from the mean. Okay, so in other words, if you take your mean and you add or subtract 1 standard deviation, you get 68% of the population covered. 95% of all data lies within plus or minus 2 standard deviations. So you go to the mean, you add or subtract 2 sigmas, that'll give you 95% of the population. And lastly then, if we go to 3, so you go to the mean plus 3 standard deviations, you'll get 99.7%. Now, these numbers have changed slightly since we did this the first time. So it's 68%, the mean, plus or minus 1 standard deviation. Yeah, 95% is the mean, plus or minus 2 standard deviations, and 99.7% of the population are found within the mean, plus or minus 3 standard deviations. So it's important from a statistical point of view that we know what the mean is and we know what the standard deviation is. Okay. So there's a picture just to demonstrate what I was talking about. There's the mean. Okay, so the mean runs down here like so. Now, If I take one standard deviation either side, I get 68%. If I go 2 standard deviations either side, 95%. And if I go 3 standard deviations either side, I go to 99.7%. And that can be done with data, it can be done with population, it can be done with anything. So it's a lovely way for me to be able to carve up a population into 3 regions and then compare statistics, whatever statistic is under review, to compare that statistic in those bodies of populations. The number of deviations of a given statistic from the mean is known as its Z-score. Now, in your tables on page 36 and 37, there's a table called Z, okay? And a Z-score is nothing more than the number of standard deviations a value is away from the mean. Now, why do we have to give it a Z-score? The answer is simple. Because if we're dealing with body weight, we're dealing with pounds, lbs. If we're dealing with height, we're dealing with, say, foot and inches, or we might be dealing with centimeters or meters, okay? If we're dealing with anything, we've got units, different units. Now, you cannot put different units onto the same normal curve. So what we do is we standardize the units, okay? So instead of talking about the mass in pounds or the height in centimeters or meters or the IQ in IQ units, we simply say, okay, let's standardize the whole lot into Z-scores. And if I can turn them into Z-scores, then I will know exactly where the statistics fall in relation to the mean. And you might say, well, how do you do that? How do you turn them into a Z-score? There's a formula, okay? And just before I come to the formula, it says a statistic with 2.4 being its Z-score is nothing more than a statistic that is 2.4 deviations above the mean. So I know straight away in this case, if I draw my normal curve like that, that anything with a Z-score of 2.4 is up here. There's your mean, and there's 2.4 deviations away from the mean. Now, because it's plus 2.4, it's to the right-hand side, okay? If an object or a statistic has a Z-score of minus 1.67, that brings it down here. Now, it's minus 1.67 deviations away from the mean. So the first thing I want you to remember about deviations is this. Positive deviations bring you to the right-hand side, and negative deviations bring you to the left-hand side, okay? And that's important when we come to using these things. So the tables, as I said already, page 36 to 37, have a table that will convert your Z-scores then into probability. So there's 3 things we've got to do. Number 1, we've got to get the statistic. What am I trying to measure? Okay. Secondly, because we can have measurement in different units, we've got to standardize the units into Z-scores. And what will the Z-scores do from the tables? They will convert that Z-score into a probability. All right, but there's where we begin. We always begin with a statistic. We turn the statistic into a Z-score. We then go to the tables in order to look at the probability. And to go from statistics to Z-scores, it's a formula. And again, that formula is on page 34 of your tables. And to go from Z-scores to probability, you go to the tables. Page 36 and 37. Okay, and more about them when we have them, because I think I have them recreated up on these slides in a moment. So remember that we always read the area that is under the curve to the left of the Z-score. Now this is important. When you get a Z-score, the probability behind that Z-score is the area of the curve that is to the left of that Z-score. All right, I'll demonstrate that here now. So let's take a look at this. Let's take, what is the probability of a Z-score being less than or equal to 1.36? Now, how do I work this out? Well, first of all, the first thing you do is you find out where is a deviation of 1.36. Well, 1.36 is roughly here. Okay, that's roughly 1.36. Now, what does it want to know? What's the probability of the Z-score being less than or equal to 1.36? Well, being less than or equal to it, that's going that way. Okay, and the lovely thing is that the tables tell me what all that area there actually is. They give me the probability, because tables can only reveal what is to the left of a Z-score. So what do? I go to the tables here. This is your Z-score. These are on page 34 and 35 and 36 and 37 of your tables. And you look down from 1.36. So there's 1.3. And then you jump across, there's 1.3. Then you jump across to 0.6, 0.06 I should say, which is there. What does that tell me? That 0.9131 is the probability of Z being less than or equal to 1.36. Now, you can write it down as 0.9131 if you wish, or you might write it down if you want to also as 91.31%. So in other words, the area that is shaded behind 1.36 Z-score is 91.31% of the entire normal curve. Okay, let me just take that off there. Okay, next one. What is the probability that the Z-score is less than or equal to 2.89? Now, in order to do that, I'm going to clear everything here. 2.89. First of all, go to your normal curve. Where is 2.89? 2.89 is up here somewhere. So there's Z equals 2.89. Okay. Now, what's the probability that Z is less than or equal to 2.89? And again, that's pushing me back in here, which is the correct way that the tables are going to tell me. So in other words, they want to figure out what percentage of that curve is now shaded if I look to the left of 2.89. So I go to the tables, I find 2.8, then I find 0.09, and I come right down onto the same column, and that's what I work out. 0.9981. That's the probability that a Z-score will be less than or equal to 2.89, or as I said already, 99.81%. You decide what you want to do. Some people stick with decimals because they make an awful lot more sense. Okay, next one. Notice that the tables only give positive Z-score readings. Now, your Z-scores go from 0 up to 3. Over here, these are all positive Z-scores. Down here, these are negative Z-scores. Notice that there is nowhere in your tables that actually take in the negative Z-scores. And the reason for that is because the normal curve is symmetrical. And if the normal curve is symmetrical, then whatever happens on the right-hand side can be reflected in the left-hand side. And likewise, whatever's happening in the negative area can be reflected in the positive area. So just to give you an idea, look at the next one. What is the probability of the Z-score being less than or equal to minus 1.65? Now, first of all, where is minus 1.65? Minus 1.65 is here. Okay, now, I want to find out what's the probability of a Z-score being less than or equal to that. So in other words, I want to work out what is the probability of being in that area there. But if I look at my tables, I don't have a minus 1.65. So this is where symmetry comes in. Okay, so instead of using minus 1.65 to the left, we go to 1.65 and we mirror that area to the right. Okay, so instead of looking at this one, which I can't do, I'm going to look at this one, which I can do. But here's the problem. If I now look at what is behind 1.65, the table will give it to me. Tables only allow you to read to the left. See? So therefore, if that's Z equals 1.65, I now want to find out what's the probability of being in front of 1.65. So I've got to change this to be greater than 1.65, thanks to symmetry. Now, how do I get the area in front of a Z-score? You can't. It's not in the tables. Tables only give you the area that is to the left. So instead, what we do is the following. I'm going to take these here away for a moment and show you. All right, so instead, we do the following. We say that the entire normal curve has a probability of 1. Okay, the whole thing together is 1. Now, if all of that is 1, and the Z-score will give me everything to the left, well then, the region to the right must be 1 minus whatever is to the left-hand side. Meaning that if the P of Z greater than 1.65 is that red region there, then the way to find it is to start with the whole curve and take away from that the probability of what is less than 1.65. So in other words, you're starting off here and you are as 1 and you're removing everything to the left of 1.65. Now I can go to the tables. 1.6 is there. 1.65 is here. So that gives me 1 minus 0.9505, which comes out as, and again, ask your trusty calculator, 1 minus 0.9505, that comes out as 0.0495, or another way to say that, 4.95%. So there's a 4.95% chance that a Z-score will be less than minus 1.65. Why? Because there is a 4.95% chance of a Z-score being greater than 1.65. So we're using the symmetry. I'll do another one of those. Okay, next one. What is the probability that Z is greater than or equal to minus 0.22? Now, think about that for a minute. First of all, where is minus 0.22? Well, minus 0.22 is going to be very close. It means there, it's about there, okay? Minus 0.22. That's the Z-score. Okay, question wants to know what's the probability of being greater than that. So we want to work out what is that shaded area there. Now, do tables, first of all, give me negative Z-scores? No. So I can't use the negative Z-score. And even if I could, tables don't give me probabilities to the right. Tables only give me probability to the left. So instead, here's what I'm going to do. I'm going to bring in symmetry, okay? And here's what I want you to think of. The area that is in front of minus 0.22 is exactly the same as the area that is behind 0.22. So if that Z equals 0.22, then thanks to symmetry, the area behind it, like that there, is exactly the same as what was in front of 0.22. Now in a situation like that, we're going to rewrite this as the probability that Z is less than or equal to 0.22. And that's perfectly fine because tables will read to the left like so. So they will give me that value. And all I've got to do is find 0.22 up there. There's 0.2 and go across to 0.22 and there it is. And the answer is 0.5871 or 58.71% chance of the probability of Z-score being greater than or equal to 0.22 or minus 0.22 in this case. Okay. Symmetry is how we did those questions. Okay. Now the first two were fine. What's the probability of being less than 1.36? Perfect. 1.36, go to the less than. Z less than or equal to 2.89, 2.89, go to the left. But when you're talking about less than a negative number, you can't get less than a negative number on your tables. So therefore, you have to look at greater than the positive form. But because the tables don't give you the right-hand side, it's 1 minus whatever is to the right-hand side of the positive form. And the same thing here, greater than the negative form. Well, I can't get greater than the negative form because I can't go to the right-hand side. So instead, I go to the left-hand side of the positive form, which the tables will give me. Now, how do I work that out in terms of using, say, examples in everyday life? Assuming that Z is normally distributed with a mean of 0 and a standard deviation of 1, let's find the following. I'm going to do this for you here. P is less than 1.22. So, less than 1.22. Where is 1.22? 1.22 is about there. So I would always put the line in. That's about 1.22. So Z equals 1.22. Okay. Now, what do they want me to look at? Less than that. So that means going this way. Perfect. Tables will go to the left. That's fine. So I go to my tables, which I have here in front of me. I find 1.22. And 1.22 on the tables is 0.8888. Okay. So in there, it's 0.8888 or 88.88%. So 88.88% chance that the Z-score will be less than 1.22. Very straightforward. Next one. What's the probability that Z is greater than 2.37? Now, first of all, find out where 2.37 deviations are. 2.37 deviations are here somewhere. Let's say that Z equals 2.37. And the question wants the probability of greater than or equal to this. Well, the only area that's greater than or equal to is that one there. but tables don't read to the right hand side. I cannot go to the right, I can only go to the left. And this is where symmetry has to come in, okay? Because that shaded region there is the same as the whole curve minus what is to the left of 2.37, okay? So I'm going to rewrite this as 1, which is the entire curve, minus the probability of z being less than 2.37. And now I know straight away what is to the left of 2.37 because the tables tell me 2.37 is 9911. So it's 1 minus 0.9911. And that's going to give me 0.0089. So there is a what? There is a 0.89% chance that we're up here. Okay, so again, I had to use symmetry in order to get me out of that one. And I also had to use the fact that tables only read to the left. Okay, next one. The probability of z being greater than or equal to minus 0.56. Okay, first of all, where is minus 0.56? Minus 0.56 is about there. So I draw my line as best I can down through that. I mark that down as being z equals minus 0.56. Okay, what does the tables want, or what's the question want me to do? Greater than, so all this area here. Now, do the tables read to the right? No. Can I get the z-score of a negative number? No. So the first thing I've got to do is turn this into something that is readable. Now listen carefully what I'm going to tell you. The area to the right hand side of minus 0.56 is exactly the same as the area to the left of plus 0.56. So 0.56 is about there, like that. That z equals 0.56. So I'm using symmetry here. And the area to the left of that is readable by the tables. So instead of using this here, I've got to rewrite that as the probability of z being less than 0.56. See that? So greater than the negative or less than the positive. You can work that symmetry in perfectly. And now I simply go to my tables. And 0.56 has a reading of 0.7123 or 71.23% chance of being less than 0.56, which also means there's a 71.23% chance of being greater than minus 0.56, thanks to the symmetry of the normal curve. Okay. Part D, the probability of z being less than minus 0.82. Now, first of all, where is minus 0.82? Minus 0.82 is about there. So again, you draw your line like so. You write down the fact that this is z equals minus 0.82. And then the question says it wants the probability of less than that. So in other words, it wants this area here. Okay. Now, it's to the left, yes, but the tables won't give me a negative z-score. Can't use negative z-scores in the tables. So instead, I turn this area to the left of a negative into the area to the right of the positive. See symmetry? Like this. So those two, those two areas should be the same, like that. These two areas here, I'll get that one in a minute. So that area there is the same as this area here. And instead, that is z equals 0.82. Now here's the problem. Tables don't read to the right hand side. Tables only read to the left. So in order to get this, let me just take the rest of these things off here. So in order to get the area that is in front of this z-score, I'm going to have to use the formula that says 1 minus the probability that the z-score is less than or equal to 0.82. Okay, 1 being the whole curve minus the probability of everything to the left, which means I'm left with the area I want. So it's 1 minus, now you go to your tables. What's 0.82? 0.82 is 0.7939. So 1 minus 0.7939 comes out as 0.2061. So in other words, there is a 20.6 0.61% chance of being less than minus 0.08, sorry, minus 0.82. Okay. There's another one. No, that's it, I think. Let me just get rid of that. Easy, apologies. Okay, let me just make sure that's the last one. Yeah. Okay, I'm going to leave you to do some. And this is just calculating Z-scores. Okay. I just want you to take page 100 and 101 and I want you to work on the Z-scores. Because before we go on to the bigger questions involving everyday examples of where we can use this Z-score phenomenon, I want you to be able to calculate them raw. So I want you to work on those questions now, and when those questions are finished, we'll check them out and we'll carry on then to the very last part of this thing, which is using the Z-scores in a natural setting of a real life problem.